All right, so I'm covering multiplication of radicals today, and this is what we use to simplify square roots, which is something that you do when you are simplifying like the quadratic formula. With the quadratic formula, if it's a real world problem, we will put the square roots in our calculator, and if it comes out to a decimal, we just kind of round. But if it's not like a word problem, then we want to put it in its exact form. And so we use the property of multiplication, kind of undoing the multiplication when we're simplifying those square roots. A lot of what I'm doing here is, going to be more than you'll see necessarily on like a quiz or doing with the quadratic formula, because that only deals with numbers. I'm going to be covering what you do when you have variables as well, but it is very useful when you go to college algebra because you will be doing this in much more depth, much more often in college algebra. So I'm just going to start with, the definitions. So the symbol that you associate with the square root is actually called a radical. And so I'll say the square root symbol or radical interchangeably. Anything that is underneath that top line is part of the radical, and we'll say it's inside or under the radical. I usually say inside because when you're typing the symbol, like in Connect Math or a math program, there's a spot like underneath it that's kind of like inside the symbol that you're clicking in. We do have variations on the symbol where there's a number kind of in the upper left, right above the little V. And those are nth roots, which then, we'll use the term radical with those. So if there's a 3 kind of above the V, that's a cube root. If it's 4, it's a fourth root. You can have any number of roots. These are not exponents on it. These are different. It's like part of the symbol. So what the square root does is that it undoes squaring a number. So if you know that 3 squared equals 9, then the square root of 9 is going to give you 3. So it's like you're asking yourself, what number squared gives me this number that's underneath the radical? And if you square negatives, you also get a positive. So the square root of 9 also can be -3. So square roots generally have 2 answers, a positive value and a negative value, because when you square, both positive and negatives give you the same thing. Now, we usually assume we want only the positive version. So that's called the principal square root because that's the one that we use the most often. So when I'm going through and taking square roots in this lesson, we're always going to have a positive answer. We're not going to say, okay, could this possibly be a negative? We're going to have the positive version. The only time that you want the negative version is when you want both, when you're solving. So that's if you're looking for a value for X. What we're doing today, we're not solving, so we don't have to worry about that. But we generally will use what's called the plus or minus symbol in front of the radical, and that's used in the quadratic formula because you're solving when you have the quadratic formula. And that symbol just means that we've got 2 answers there, the positive and the negative version. And your calculator always assumes the positive because that's generally what we're usually working with. So you do have to be aware, okay, I also have to give the negative, what I'm solving. You do have to know when you need both numbers and when you don't. But everything we're doing today, you only need the positive. And so I mentioned the radical, you could have cubed roots and fourth roots. Those are just undoing other exponents. So the cube root will kind of undo or reverse a exponent of 3. Fourth root undoes exponent of 4. And so that's that symbol that we use. We just put any number kind of up above the V, and we call n, that number, the index, and then the thing underneath is called the radicand. We're going to be focusing just on square roots in this lesson. So you don't have to worry too much about this other than just knowing that there are other types of roots. And this is where in college algebra, you'll focus on the other types. You won't be restricted to just square roots. You'll be looking at cubed roots, fourth roots, and using those much more often. And then the last thing before we actually start getting into what we're going to do is when you have variables, a square root divides the exponent by 2. If you have a cubed root, it divides the exponent by 3. So when you're taking roots of variables, you're just dividing by the index. And so we are going to be using this when I go through here, use this rule where the exponent divides by 2 when you're taking a square root. But again, when you get to college algebra, you'll be doing this in much more detail. So this is kind of like we're introducing you to the most basic level of radicals, and the college algebra will take that and kind of go a step further. So multiplication property of radicals. So if you are multiplying 2 radicals, and they could be square roots, they could be cube roots, anything that has that symbol, when you're multiplying them, if they have the same index, so they're both square roots or they're both cube roots, then you can combine them into a single radical. So you basically multiply the things inside together to get to combine them. So when we're simplifying, we're going to use this because we always give our answer with a single radical. We don't leave multiple radicals in our answer. And we sometimes when we're simplifying, we will go the other direction temporarily to simplify further and then recombine it again. So we use this property extensively in order to simplify a radical. And simplifying a radical just means you want as much as possible out of the radical symbol, like not inside, but try to get as much as you can outside of it because it's easier to work with. So going through the examples here. So we've got, these are quicker examples. Your directions just say multiply. Now, even if it says multiply, it's always assumed you simplify further. Even if it doesn't say simplify, if you can, you want to simplify your radicals. So you always try to simplify, even if it doesn't specify. So we'll start with the top left. So when you're multiplying these square roots, you combine them into a single square root symbol, single radical, and you multiply the numbers that are inside, the 7 and the 6. So when we multiply these, 7 times 6 is 42. So you get the square root of 42. Once you combine it, then you need to ask yourself, can I simplify this further? And so that means, is there a perfect square that I can divide out of this number? So perfect squares are numbers we can take square roots of. 4, 9, 16, all the things that are squared, something squared. So you ask yourself, okay, can I divide 42 by any of those numbers? 4, 16, 9, 25, 36. So knowing your perfect squares is really important. So none of those go into 42. So that's just your final answer. If you can't divide it out by one of those, then you're just done. And you've done your job. You've multiplied it. You combined it to 42. So on the right here, we've got the square root of 59 times 59. So, or the square root of 59 times the square root of 59. So you're basically multiplying 59 times itself. And instead of actually doing that multiplication on the calculator, I'm going to write as 59 squared because that's what we're doing. 59 times 59 is 59 squared. And that square root cancels out exponents of 2. Or if we're simplifying, you divide the exponent by 2. So that square root and the exponent of 2 basically cancel each other out, and you're only left with the 59. And so that's your final answer here is 59. So we did more than just multiply the numbers together. We need to see if it's possible to take things out of the square root or take the square root of your result. You can also, if you've got your calculator, just, multiply 59 times 59, which gives you 3,481. And on your calculator, if you take the square root of that number, you'll get a whole number, you'll get 59. So that means, okay, I can take the square root, I'm going to do so. That's my final answer. Now compare this to the square root of 42. If you put the square root of 42 on your calculator, you get a decimal. So that doesn't come out to a whole number. So you want to try to make things, if they can, if you can take the square root and it gives you a whole number, you want to do that as much as possible, because it's just much easier to work with whole numbers than to work with square roots. Bottom left, we've got t. So this is very similar to the one we just did with the square root of 59 times square root of 59, but we've got t inside our radical, square root of t times square root of t. So t times t, again, this is just t squared. That square root symbol, the radical, cancels out the 2. And so these cancel out and you get just a single t as your answer. I said when we're simplifying radicals with exponents that if it's a square root, you divide the exponent by 2. So 2, the exponent on the t divided by 2 is 1. So we have one single t there when we take the square root. So when we simplify that. Now, bottom right here, I've got the square root of 2 times the square root of 10. So we start by multiplying that together. 2 times 10 is 20. And if you had your calculator, you took the square root of 20, you're going to get a number with a decimal. So we can't just make this a whole number. But like we did with square root of 42, we want to see, can I divide that number by a perfect square? So like 20 divided by 9 or divided by 16. Well, neither of those go in there, but I can divide 20 by 4. So to simplify this further, we're going to actually do the multiplication property again, but we're going to split it up. So we're going to split kind of that square root of 20 up as the square root of 4. And 20 divided by 4 is 5. So that's going to be the square root of 5. So we used our multiplication property to combine it to a single square root. But to simplify it further, we're using the multiplication property to split it up again, kind of going backwards, but we're splitting it up differently. We're splitting it up in such a way that one of these things comes out to a whole number. The square root of 4 is 2. So you can actually take that square root of 2 or square root of 4 to get 2. And then you have the square root of 5 left over. And square root of 5 can't be split up. There's no perfect square that divides into it. And so your final answer is 2 times the square root of 5. And we consider this simpler than our previous answer because we've got whole numbers we're able to remove from the radical. And we made the number inside the radical smaller. So not every number can be simplified. 42 could not because we couldn't divide it by a perfect square, but 20 could be. So your procedure, you have to kind of go through when you're simplifying these or when you're multiplying, the first step is always to multiply. But if you can take the square root of it, you do. If you can't, then you have to see, well, can I split it up in such a way that I can take the square root of some of it? And if not, then you leave it where it is. Otherwise, you do try to do that and simplify further. So there are questions on any of these 4 examples. Okay. So those were the most basic type. And now we're going to kind of, combine them. So multiply the expressions. And here now we've got square roots, but we also have numbers in front of the square roots. So remember our commutative property of multiplication. So the commutative property of multiplication says that the order of multiplication doesn't matter. You can rearrange the order that things are multiplied. And so that's what we do here. We rearrange it so that the whole number parts, the parts that are outside of the radical, get multiplied together. And then the things that are inside the radical get multiplied together. So instead of 4 square root of 2 times 5 square root of q, you rearrange it so that you have 4 times 5, and then your square root of 2 times the square root of q. So we're just using the commutative property and then the associative property to just kind of rearrange what's in parentheses here. So you're multiplying your whole number parts and then you multiply your radical parts. So 4 times 5 is 20. And then in the square root part, we multiply 2 times 2, or q is 2q. So the number in front, once you've multiplied that, you just kind of leave it there. Inside the radical, then you want to say, okay, can I simplify this further? So we look to see 2. Can I take the square root of 2? So you can't, because it gives you a decimal. You'd have to round it. And no perfect square goes into 2. So that stays. And then you look at the variable. Does the q have an exponent I can divide by 2? If it doesn't, then it just stays there. And so we can't simplify inside the square root any further because we can't kind of split up the 2. We can't do anything with the q. So that's your final answer here. So we multiplied the whole number parts at the front, and then we multiplied the square root parts together. So problem on the right is very similar. Now we don't have a variable here, but that's totally fine. It's the same process. So I've got -6 times the square root of 2, and then a negative times the square root of 22. That negative is basically a -1 times the square root of 22. So we're going to rearrange this one as well. So it's going to be a -6 times a -1, and then the square root of 2 times the square root of 22. So -6 times -1 is 6. And then we multiply our square roots. 2 times 22 is 44. So now you want to say, can I simplify the square root of 44? So when you put that in your calculator, you'll get a decimal. So then you say, okay, it doesn't come out to a whole number, but can I divide that by a perfect square? So 44, let's see, you want to try the biggest numbers possible. You don't want to start with a small one. So the first perfect square under 44 is 36. So does 36 go into 44 evenly? The answer is no. So then you're like, okay, 44, let's divide by 25. It doesn't divide by 25. So then you're like, okay, next one would be 16. Does 44 divide by 16? No. So then you're like, okay, next one underneath that is 9. Does 9 go into 44? No. And then you try 4. Does 4 go into 44? Yes. So you want to know your perfect squares. 4, 9, oops, I missed 16, 25, 36. So that's 6 squared, 7 squared is 49. Like, you want to know those numbers, and you always try the biggest one first because that will save you time. So 4 is the only one of those that's smaller than 44 that can go into it. So I still have my 6 in front, and we're going to split this up as square root of 4, and then 44 divided by 4 is 11. So 11 can't be divided by any of those perfect squares, so that can't be simplified. We can take the square root of 4, that is equal to 2. So all of these it's implied multiplication. You don't see the multiplication symbol there, but it's implied that it's multiplication. So this 6 is going to be times 2 when you take the square root of 4. And then you have your square root 11. So then we're going to do our multiplication of 6 times 2, which is 12. And so our final answer ends up being 12 times the square root of 11. So the one on the left, I mean, you start out doing the same sort of step, but if you can't simplify in the radical, you're done. But on the right, we could simplify that 44 up to 4 times 11. So we can split it up in a different way that allows us to simplify further and get a smaller number inside that radical. Are there any questions? Okay. So we'll do some more here. On the left, I have 4y and then the square root of 3 times the square root of 6. So there's no number in front of the square root of 6. So I don't really actually need to do any rearranging because that 4y is just, I'd be multiplying by 1. So all you need to do is just use your associative property to rearrange your parentheses here. We're doing the square root of 3 times the square root of 6. So we get 4y and then 3 times 6 is 18. So now you ask yourself, does a perfect square go into 18? So, again, I'll write my perfect squares here. I always skip 1 square because it doesn't really mean anything. You definitely want to have these memorized, but you can write them down until you do. So the first perfect square that's smaller than 18 is 16, but that doesn't divide evenly into 18. The next one is 9. 9 goes into 18. So we can split this up as the square root of 9, and then 18 divided by 9 is 2. So that's times the square root of 2. So the square root of 9 we can take, that is equal to 3. So this is going to be 4y times 3 and then the square root of 2. And then just like when you have things with variables and coefficients, you multiply the numbers together. So 4 times 3 is 12. So we get 12y and then the square root of 2. We always put our numbers and variables in front of the radical because if you put it in the back of the radical, sometimes if you are not very clear with your handwriting, it's hard to tell whether the stuff is in or out of the radical. So like if I had written 12 square root of 2 and then a y, it's like if you were kind of messy with your square root, you might be wondering, is that y in or outside the radical? If you're not very clear with where your radical symbol ends. So we like to put the variable in front of the radical so it's very clear that is not inside the radical. Now let's look at the second example here. We've got 1/4 u times the square root of uv and then times 8u as square root of v. So we're going to rearrange it and you can put the 1/4 times 8 together. We've got our u times u together because the 1/4 u and the 8u, I can multiply those u's together. And then we've got the square root of uv times the square root of v. So if you wanted to, you can put in parentheses 1/4 u times 8u. I mean, we're familiar with how to multiply that, but you know, you can also split it, put the numbers together, then the variables, and then the square root. So 1/4 times 8 gives you 2. U times U is U squared. And then when I multiply inside the square roots, I have a U V times a V. So the two V's get multiplied together to get a V squared. So we get 2U squared and then the square root of UV squared. When you have variables, if it's an exponent that you can divide by 2, then you want to kind of split it up. So I've got 2U squared. And I'm going to split this up, and I put my V squared first and then my U. So just like we did with the numbers where you split it up into something you can take the square root and the leftovers, we do the same thing with the variables. So the V squared I can single out because I can divide that exponent by 2. That means I can take the square root. But the U I can't, so that's just kind of there. So the square root cancels out the 2. And so we're left with just a single V when you take that square root. So you get 2U squared V times the square root of U. So when you take the square root, that exponent is divided by 2. 2 divided by 2 is 1. So I have 1V that's outside of the radical. And then the only thing that's left over is a single U. Are there questions on either of these two examples? Okay. I think I'm going to skip these and go to these. The last slide, it's more of the kind of the same. And if there's no questions, then I can skip it. So we can go into the little harder things here. So again, we're multiplying. Instructions are a little different here. It also says assume the variables represent positive real numbers. We had variables in the previous ones. We always assume that they're positive real numbers, even if it's not specified. And that wording just says, hey, you're not going to get any, you don't have to worry about getting the negative part. That's all that wording is saying. Whether it's stated that there or not, you always assume that you're going to get a positive out. So we've got what looks like the distributive property here. Square root of 2, and then in parentheses, square root of 6 minus the square root of 3. The distributive property works even if you've got things with square roots. So you still distribute. So you're going to have 2 times the square root of 6. And sometimes it helps to actually write that out. And then you're doing 2 times the square root of 3. And I've got a minus sign there. So it's minus square root of 2 times the square root of 3. So that square root of 2 is getting multiplied by both of those things. So once you've written that, then you actually do the multiplication and you combine them into a single radical. So 2 times 6 is 12. So we get the square root of 12 minus, and then 2 times 3 is 6. I will often do this in my head. Like I will skip that first step that I wrote down and I will do the second one in my head. But it's, it's good to write that first step down when you're first learning how to work with these things. So we've got these radicals. We cannot just subtract these because in order for them to be considered like terms, the inside of the radical needs to match. So because the numbers on the inside don't match, these cannot be subtracted. What we can do is try to simplify each radical separately. So like the square root of 12, I can simplify that because I can divide 12 by 4. So I can pull out a perfect square and simplify that further. So that's the square root of 4 times the square root of 3, because 4 times 3 gives me 12. And then I've got minus the square root of 6. So the square root of 4 is 2. So you get 2 times the square root of 3, and then minus the square root of 6. And I didn't try to simplify the square root of 6 because it can't be. I can't divide 6 by 4. So it doesn't get simplified further. So we've got 2 square root of 3 minus square root of 6. And these cannot be subtracted because there's different numbers in the radical. So they are not like terms. So you do end up with an answer that does not necessarily look simpler, but it is considered simplified based off of our rules. So if we do the one on the right, again, it's going to be using the distributive property. So I've got 4 square root of x, and I'm multiplying that by the square root of x. So I'm going to just write that down. And then I've got a plus, and then 4 square root of x times 5. So I'm going to just put that in parentheses so that it doesn't look like it's in the radical. So now we're going to do our multiplication. So I've got 4x times x is x squared. So that's inside the radical. Plus, and then I can multiply 4 times 5, which is 20, and then I have square root of x. And then you want to try to simplify each part further. These can't be added because there's different things inside the radical. And x squared is not the same as x. So the square root of x, we can cancel that out and you're left with a single x. So you get 4x. I think I said the square root of x. Square root of x squared. The square root, those cancel, you get x. And we can't do anything about the square root of x because it doesn't have an exponent I can divide by 2. So it just stays where it is. Now I have an x in both terms, but one is outside the square root and one is inside the square root. They are not like terms. So they have to match exactly. And because one's inside, one is outside, they're not considered like terms. So that's your final answer. Are there any questions on these two? Okay. So same thing, we're doing the same thing here, but now instead of the distributive property, we are going to FOIL because we have 2 things times 2 things. So FOIL, just like you had with polynomials, the same rules work for if you've got things with square roots. So I've got 8 times the square root of 7 minus the square root of 5, and I'm multiplying that by the square root of 7 plus 3 square root of 5. So we're going to do FOIL. First, outside, inside, last. So first is 8 times the square root of 7 times the square root of 7. Outside, we've got 8 square root of 7 times 3 square root of 5. Inside is minus square root of 5 times the square root of 7. Probably should give myself more room here. And then last is a minus square root of 5 times 3 square root of 5. So I'm actually going to just duplicate this slide and do the second problem on a new slide because I'm clearly needing more room. So, okay. So once you've written out the FOIL, first, outside, inside, last, you need to do that multiplication. So I've got 8, and then 7 times 7 is the square root of 49, or you can write it as 7 squared. So we can do it that way. Plus, I've got 8 times the square root of 7, and then 3 times the square root of 5. So if you want, you can rearrange that. So we're doing 8 times 3, and then the square root of 5, or the square root of 7 times the square root of 5. Just, to write it so you know what you're doing here. The square root of 5 times the square root of 7, you can combine those. 5 times 7 is 35. And then I've got a minus, and then square root of 5 times 3 square root of 5. So the 3 just kind of goes in front because the square root of 5 would be a 1 in front of there. And then 5 times 5 is 25. Or you can write that as 5 squared. So let's go back to the left. We've got 8. The square root of 7 squared. So it's a square root of 49. That gives you 7. Because the square root cancels out the exponent of 2. So that's going to be 8 times 7. It's assumed multiplication. It's implied multiplication. 8 times 3 is 24. And then the square root of 7 times the square root of 5 is the square root of 35. 7 times 5. Then I've got minus the square root of 35. And then minus 3 times 5, because the square root of 5 squared is 5. So 8 times 7 is 56. I have plus 24 square root of 35 minus square root of 35. So those are like terms because they both have square roots that are the same thing, same number inside there. So those are like terms. These we can do subtraction for. And so you assume there's a 1 in front of the radical if there isn't a number there. So what you do when you combine these is you take the whole number parts that are outside and you do the math. 24 minus 1. So that gives you 23. And then the square root parts don't get subtracted. They just stay there. So you don't do 35 minus 35 and get 0. It stays the square root of 35. So when you're adding or subtracting radicals, the radical part acts sort of like a variable. So when you're adding like 24x minus 1x, you get 23x. So the variable is, and the square root of 35 is like an x. It just kind of hangs out there. And then I've got this minus 3 times 5, so that's minus 15. So now you keep going. We still have like terms. 56 minus 15 is 41. So we have 41 plus 23 times the square root of 35. And 35, you then say, okay, can I simplify this? Can I divide it by a perfect square? So you try them. 25 doesn't go into that. 16 doesn't go into it. 9 doesn't divide into it. And 4 does not divide into it. So you can't simplify that further. So that stays. And this is your final answer. And this is kind of what your final answer looks like when you use the quadratic formula, is that you'll often end up with like a whole number plus something with a radical or minus something with the radical. So it's kind of a lengthy process. You want to make sure that you write every step because you have to go through FOIL and then you need to multiply the things appropriately. Then you need to add your like terms correctly and keep going until you can't go any further. Are there questions on this example? We'll do the second example on the next slide. Okay. So now we'll do the second example here. We have 11 times the square root of m plus 4n times the square root of m plus n. So FOIL. 11m times the square root of m. So I'm going to just write that out. Outside is 11m times n. And I put that n in parentheses so it doesn't look like it's in the radical. Inside plus 4n times the square root of m. And then last plus 4n times n. So once you've written down what you're multiplying, then you actually multiply. So m times m is m squared. So I got 11 times the square root of m squared plus 11 square root of m times n. So what happens is that n is outside of the square root, so it doesn't get multiplied by the m, and it gets multiplied by the 11. 11 times n is 11n, and then I have my square root of m. So it's kind of, we're just rearranging things there. Then I have plus 4n times the square root of m plus 4n squared. So now I start over from the left, the square root of m squared. So the square root cancels out an exponent of 2, and you're just left with m. So I have 11m plus. Now these middle terms are like terms. And they are like terms because they have the same variables in front of the radical and the same thing inside the radical. So for like terms, everything has to match except for that coefficient. So if one of these had an n on the outside and the other one did not, they're not like terms. If one had the square root of m and the other one didn't, they're not like terms. They have to match with the variables in front and the stuff on the inside. So because those are all the same, these are like terms, and so you can add the numbers 11 plus 4, which is 15. So you get 15 n times the square root of m. So the variable parts and the square root parts, those just hang out, they don't get added together. And then I have this plus 4n squared. So then you go again from the left and you're like, okay, do I have any like terms? Because like here we had numbers that we can add it together, 56 and the minus 15. So I was able to combine those further. Here I don't. So I've got an 11m, but I don't have anything with just m by itself. So there's nothing to add that to. I've got an 15n square root of m. So there's nothing else with square root, so I can't add that to anything. And then I have an n squared, and there's nothing else with n squared. So that can't be added to anything either. So this ends up being your final answer, which yes, it does look kind of messy, but this is considered simplified. Are there questions? Okay, and then this is my last one. I knew this one was going to take up space, so at least I didn't try to put 2 on this one. We've got 5x minus the square root of x, so that's 2 things. But now we're multiplying by 3 things, x plus 5 square root of x plus 6. So this is not FOIL. So I usually make a table when I see something like this. Because if I try to do all of my arrows, I kind of get lost. So I make a table. So across, I like to make the long part on the top of my table. And then I make the shorter part go down. And then I make sure that minus has to go with that square root of x. So I'm going to use a different color to fill in my table here. And now you multiply your row by the column. So 5x times x is 5x squared. Then I have 5x times 5 square root of x. So 5 times 5 is 25. The x is outside of the radical and the other one is inside. So those just kind of get written together because they can't, if one's outside, one's inside, they don't really combine. Then 5x times 6, that gives you 30x. Now, next I have a negative times a positive. So I'm going to get a negative, and then I have an x and a square root of x. I'm going to put these in the same order as the other x and square root of x. Then I have a negative square root of x times 5 square root of x. So a negative times 5 is negative 5. And then the square root of x times the square root of x becomes x squared. So I do that multiplication mentally. And then I have a negative square root of x times 6. So negative times 6 is negative 6. And then I have a square root of x. So once I've filled in my table and made sure that I haven't missed anything, then I try to, I write it all out. And I do want to point out that if you have like terms, they tend to occur on diagonals. So those are like terms because they both have an x and then a square root of x. This next diagonal here, these are like terms, but we have not simplified that yet. So those will be like terms. And so when I write this, I tend to kind of diagonal or do a zigzag so that I can kind of group my like terms together. So I have 5x squared and then plus 25x square root of x. And then I'm going to write my minus x square root of x. Then I'm going to go back up and do my plus 30x. And then the minus 5. And then the square root of x squared is x. So I'm going to just simplify that at the same time. And then minus 6 times the square root of x. So now I've got, these are like terms. And these are like terms. And so this has all the x squared of x, just that's a 1 in front of there. So when you're working with the numbers, the coefficients, you can see that. So I've got 5x squared. And then with my like terms, I just work with the numbers in the math. 25 minus 1 is 24. So it's going to be plus 24. And then I just have x times the square root of x hanging out. And then 30x minus 5x. So 30 minus 5 is 25. So it's going to be plus 25x. And then I have minus 6 square root of x. And so just be careful because these are not like terms right here. They both have the square root of x, but one has an x outside of the square root, the other one doesn't. So those are not like terms. So they have to match kind of everywhere there except for the number. And so those are not like terms. And so I can't add those together even though they may look similar. And then the 5x squared and the 25x, those are not like terms either because the exponents are different. So this ends up being your final answer here. So you have 5x squared plus 24x times the square root of x plus 25x minus 6 square root of x. So when you multiply, if you have a lot of things going on, it's helpful to kind of make a table and just be very, work very slowly when you do these so that you don't accidentally mess something up. And the types of problems like this one that I just did, that's something that if you're going into engineering, if you have to take calculus, the ability to do a multiplication like this is helpful, because when you're doing calculus, sometimes it's more helpful to multiply something out than to leave it in its multiplied form. You need to kind of know how to go between one form and the other, when one form is useful, one's not. So this is just a skill that's really helpful for those that do have to take calculus. And it's just good practice of your algebra skills, because you're using the same skills that we did earlier, with our multiplication of polynomials. We're just extending it to include square roots of things, but the rules are all the same. So we're just reinforcing that you're doing the same rules over and over and over again. We're just adding little tweaks to them. And so it's just the more you do this, the more practice you get on those rules. So there are any questions on this example? All right, so that's multiplying radicals. The main, like I said at the very beginning, when you're doing stuff with the quadratic formula, you're mainly going to be working with simplifying things with square roots of numbers. So like the square root of 20 kind of thing, you're mainly going to be simplifying something like that. You're not going to be doing so much with the variables until you get to college algebra, but it's good to just see it, understand how it all works, and realize that they're all basically following the same rules, whether it's a number or a variable. And just kind of knowing the procedure.